Hey viewers, welcome back to our channel. Hope you are doing extremely well. So today we are going to discuss another interesting question on the topic of binary tree. That is nothing but top view of a binary tree. So without wasting time, let's move on to the question. So in this question, we are provided with a binary tree and we need to tell all those nodes. Okay, we need to tell only all those nodes data which will be actually available to the viewer if we look at from the top of a binary tree. Okay, so the prerequisite for this question is the level order traversal of a, not the level order, actually the vertical level order traversal of a binary tree and the width of a binary tree. It's my request that if you haven't watched that video, please go and watch that video, because unless until you don't get the concept of that vertical level order traversal and the width of a binary tree, you will not be able to solve this question. Okay, because here what I will do, I will just tell you how this question is actually related with that, and after that we will directly move on to the code. If you don't know how that question code works, you will not get this problem. Okay, so without wasting time, let's move on to the question. Okay, so here in this question we are provided with the binary tree. Let me create a new binary tree here. Okay, so binary tree. So at first I'm taking my root value as 3 and its left value as 1 and right value as 6. Similarly, moving further, its left value is 0 and right value is 2. Similarly, this node left value is 5 and right value is 10. And for this 0 there is no left. For this 2, no left right. Okay, no left right. For this 5, I'm assuming it is 4, 15. Okay, wait. For this 15, okay, 15, 9, 11. Okay, 9, 11. It will be 12 here, 13 here, and 14 here. Okay, now this is the binary tree which we are provided. What is happening with this binary tree is that someone is looking at this binary tree from here. Okay, someone is looking at this binary tree from here, and we just need to store all those nodes which are actually available to the viewer, which is which nodes will be this viewer will be able to see. We just need to store all those nodes in a vector, and we just need to return them, and we just need to perform this in this function. So let at first figure out that what are all the nodes which the viewer will be able to see it. Okay, wait, yeah. So what if I say that viewer only will only be able to see 0, 1, 3, 6, 10, and actually it was 11 these nodes. You might be thinking that why only these nodes, like the whole binary tree is available to the user. There may be possibility he will be able to see 12, 5, 59, but why he can't see these nodes? It is just because this 2 and 5 are actually residing at the same position. That means they try to overlap each other, and the moment they overlap each other, they combine together. Okay, this combination is actually get hidden by the 3. Okay, a node having the data 3, just because that node actually reside before this combination in a straight line. Okay, if I create a straight line, if I assign them in an order, then I come to know that there may be a possibility that both of these 2 and 5 will try to fight to come at first, or they combine together. Okay, means they choose some position for each other, but that combination are actually get hidden by these 3 nodes, just because at a straight line these nodes, this combination of this node are actually hidden by this 3. Similarly, this 15 and 9, both of these nodes will be hidden by the 6 node. Okay, or and the same thing happen for the remaining nodes. Means we can say that only those nodes which actually lies in the outer periphery of a binary tree, and those nodes which are not hidden by any other node. Okay, means this 0 node are actually not hidden by any node. This 3, 1, 6, 10, and 11 are not actually hidden by any other node, are the nodes which are actually available to the user, which he will be able to see from the top. Okay, now you might be thinking that how this question is actually related with the vertical level order traversal. Okay, so now what we'll do, at first we will write the vertical level order traversal for binary tree, and after that we'll figure out how this question is related with that. So again, my request is same. If you haven't watched that video, the link of that is in the description box. Please go and watch it. Okay, and if you have watched it, let's together write the vertical level order traversal. So we know for the vertical level order traversal we will create this horizontal straight lines. Okay, So let me here also create those lines. Okay, this line will be a tilted little bit, but like this. Okay, so we know that we stores our there is an vector of vector which stores the value of for each index. Okay, means each level, the lines which we have created, these represents as a level, and each line shows some each line shows some level. So this node reside at level 0, and all those nodes which are lying on the left hand side of the node will get decremented by -1, means shows it is at level -1, it is at level -2, and all those nodes which are lying on the right hand side, their level will be nothing but +1 to the level of the root, that is +1, +2, and +3. Okay, so these are the values which we assign to some of the levels of this tree. Now let's try to find the level order traversal, vertical level order traversal of this tree. So we know that in the vector our indexing starts from the 0. That's why here I'm writing the indexing as 0, 1, 2, 3, 4, 5, and for at each position there is another one vector which stores the values that lies for that particular index. Now you might be thinking that in the binary tree here my indexing is negative, that is it is minus n to the plus n, but here in the vector my indexing is positive, it is greater than or equals to 0. Why is it happening? If you don't know, if you don't get it, then it's my request, go and watch that video, just because there is a dedicated video which is explaining the whole concept of vertical level order traversal. Here I'm doing nothing, I'm just writing the vertical level order traversal. So here I was working on finding the vectors. Okay, so at the position 0 means this -2 shows means this -2 get mapped to this 0 position. Okay, so at the level 0 there is nothing but 0 node will be present for this 1, 1, 4, and 13. 1, 4, and 13 will be present for this 2, 3, 2, 5, and 12. 3, 2, 5, and 12 will be present for 3. The 3 represent 6, 15, 9, and 14. 6, 15, 9, and 14, it represent this 4 represent 10, and this 5 represent 11. Okay, so this is the vertical level order traversal, this is the vector of vector. Okay, so so now again, if you have watched the vertical level order traversal, then there may be possibility you get the how it helps us to achieve the top view of Binarytree. But if you have watched it but still you will not be able to how to figure it out, let's understand it. Okay, so our question is top view for Binarytree. Now again I will ask that what are all those nodes which will be available to the user when he or she will watch the tree from the top. So I will write some nodes like 0, 0, 1, 3, 6, 10, and 11. These will be nodes. Now again I will say that look at the vertical level order traversal. This the nodes which are getting into the vertical level order traversal, these nodes are nothing, means according to our question, if we update this node in such a way, that means the moment we get any node at a particular level, we just store it, and the moment we start getting another nodes at that level, we just ignore it, we get nothing, we get the top view of a Binarytree. There may be a possibility you don't get it. Let's again try to understand. Okay, let's again try to understand. Well, what if we are finding the vertical level order traversal, and at any point of time, I mean, obviously we are finding the vertical level order traversal for each level, we get the array list of array list array list of array list, because there are so many nodes residing at particular level. But the moment I get the first node at that particular level, means here for this level 0 I get this 3. The moment I get this 3, I can see that this is the node which will be available to the user. Okay, similarly for all the other levels, the moment I get the first node, I will just store it, and I will discard all the other remaining nodes which I get during finding the vertical level order traversal, and the output which I get and the loss in my vector is nothing but the top view of a Binarytree. Why I'm saying all this? Just because let's try to understand it. Okay, top view of a Binarytree is nothing but all those nodes which are available to the user if he or she look from the top. Okay, and we have already discussed that those nodes which don't hinder itself, which are not get hindered by any of the other node, and which are actually lies on the outer periphery of a binary tree. These are the nodes. These nodes are nothing but the top view of a binary tree. So here you can see the moment I'm finding the vertical level of the traversal, I'm finding each node on each line. The moment I came across any of the single node, I can say I will just add it, and the moment I get another node at the same level, I just discard it, and at last I will get this 0, 1, 3, 6, and 10 and 11 as my top view of a binary tree. So I hope you get it. So let's again try to dry run this problem using a queue data structures and the vector of vector data structures. Okay, and this time I'm not going to create a vector of vector. Why I'm not going to create a, because earlier we were creating vector of vector just because at that time we need to show all those nodes which are actually lies at a particular level. But here we don't need to show all those nodes which actually lies at a particular level. We just need to show that first node which actually lie at that level. Okay, or we just only need to show the first node. So here we have created a queue. At first what we'll do, we will just put this 3 into the queue, and we will, after putting this 3, yeah, okay, I just forget to mark the indexes of this vector is nothing but 0, 1, 2, 3, 4, 5, and this -2. This -2 index is actually mapped to the index 0 in the vector. Okay, at first what I'll do, I'll put the root in my queue. I'll just remove it. Okay, after removing it, I update it into its respective level, that is nothing but this 2, and I will add its value into the here. Now let's move forward. I'll add its children, that is nothing but this 5 and 6, sorry, this 1 and 6. I'll perform the same operation. I'll remove its children. Okay, I'll remove this one. I'll update this one at its respective level, that is 1. Okay, and after removing 1, I'll add its subsequent children, that is 0 and 2. Moving forward, I get this 6. I'll remove this 6 and add this 6 to its respective index or respective level. Okay, that is this 3. So let me update value here. Again, as we have removed the 6, let me add its children, that is nothing but 5 and 10. Okay, now again let's remove 0. Let's update this 0 at its respective level, that is nothing but 0. And as it don't have any children, we don't need to add anything to the queue. Now we get this 2. Okay, let's remove it, and as you can see that we can't update at the level or at the vector where this 2 resides. Okay, just because the level which this 2 resides, at that particular level there is already some value which we can't update it. Okay, because there is some another node which lies before this 2, and that node have already updated the value of that particular level. So means we can't change it just because we get another 2 or we get another node, because we need to store only the first node value into the vectors, and we have already get it. So what we do, we just discard this 2. Moving forward, we get this 5, and for the same thing, like we discard this 5 for the same reason, just because we can't update at the particular level position, at the particular level value of this 5, just because because there is some node which have already put its value into that particular level. But we need to add its children, like it has some children, that is 4 and 15. So we need to add its children. So we added children, we have discarded this 5. Let's move forward. We remove this 10. Okay, after removing this 10, we get what we'll do, at first we update it at its respective level. Okay, we have added its value into the level number 4. Moving forward, as we remove this 10, we need to add its children, that is nothing but 9 and 11. Remove this 4. This 4 can't update any value in its respective level, just because at the -1, that is at the level 1, some value is already present there, so discard it. And even 4 don't have any of the children. Similarly for the 15 don't have any children, and even 15 can't update any value, so discard it. Moving to the 9 have some children, but 9 also can't update any of the children, any of the value at particular level into the vector. Okay, so 9 have some children, left children, that is we have added the 12. Removing this 11, we need to update 11 at its respective level, so we update the value at the level 5. Okay, just because at the 5 there was null. Okay, okay, we have worked on the 12, 13 and 14 actually worked in the same way. They can't means they can't update any value, just because at their respective levels some values are actually already present there. Okay, and as they don't have childrens, we just need to discard them. So that's all for this explanation. I hope you get it. How vertical level order traversal help us to achieve our top view of a binary tree. So let's move on to the Pepcoding portal and let's try to write the code in the C++. Okay, so the first thing, okay, yeah, so let me increase this screen size. Okay, the first thing, what will be your first thing? The first thing is that we will calculate the width. Okay, just because I will write my favorite function, that is the width function. Yeah, one more thing is that I'm not going to explain how we are calculating the width, just because there is already a dedicated video which lies on the YouTube on our channel. If you want to know how do we calculate the width, please go and watch it. Okay, and if I started explaining all this concept in this video, it will not be worth it at all. Okay, moving forward, tree node root, it have some parameter that is HL also, and the other parameter that is the vector of int reference answer. Okay, so if root is null, if root is null pointer or null pointer, what we need to do, we just need to return. Okay, otherwise answer 0 will be nothing but min value of something, and answer 1 will be nothing but max value of something. Okay, so min value of HL and answer 0, and max value of HL and answer 1. Now we have calculated answer 0 and answer 1. What we need to do, we need to recursively call this function width and width. Recursively call to the root left, root left, and root right. Along with this, I also need to pass some other parameter, that is HL minus 1, as we are moving to the left side, and answer will remain same, and HL actually, and HL plus 1 as we are moving toward the right hand side. The another thing is the pair. Okay, as the Java language don't have the pair data structures available itself, so we create a pair class, but in the C++ we have a pair data structures. Okay, so we use that which is available as STL, that is standard template library. We are going to use it. Okay, so type def type type def pair tree node star int and pairs. Okay, that's all. Let's complete the function of vector top view. Okay, so what will your first thing which we need to create, that is the queue. Sorry, so the first thing is the queue which we need to create. So we'll create the queue of pairs. It is a queue. Okay, so again we'll calculate the vector. What this vector store? This vector will store the data of the value of the answer. Okay, min max, vector min max, actually max, min max of size 2. Okay, we have initialized this size. Now we need to call the function width, which will update the value of this vector. Okay, so root 0 min max. Now moving forward, we need to calculate the length, that is min max 1 minus min max 0. Okay, so for int I equals to 0, I is less than length, I plus. Now I am putting the default values on each and every position. I is less than equals to length. I am putting the default value into my each and every index of the vector answer. Okay, so I am putting the default value as int 1e9. That is nothing but but the maximum range of the integer value. Now what we'll do, we just need to add the first value into the queue, that is nothing but a pair of root and minus min max 0, min max 0, min max 0. So now we will do two loop. We will here perform two loop. Q dot size is not equals to 0, and the another loop, that is, if you are not getting what I'm writing, then please go and watch vertical level order traversal, just because the code is same that we have explained there. It is like here I'm not writing anything new, I'm just writing the code of vertical level order traversal. Int sz equals to q dot size. Okay, q dot size, again another loop, that is we okay, so sz minus minus is greater than 0. This loop will iterate, call this, and let's remove the top value, the front value from the queue, that is the q dot front. And after removing that from the queue, let me after getting that value from the queue, let's remove it. Okay, that is the pop, q dot pop. Now we need to check that whether at that particular level, okay, for that particular node at that particular level, whether the value is the default value. Second is the default value, that is int 1e9. If the default value is present, what we need to do, we just need to update it with the initial value, that is the rp dot second goes to rp dot first value. Otherwise what we need to do, we just need to discard that value, but before discarding that value, we need to add its left and the right child. So let me check whether its left and right child exist or not. Dot first dot first first left is not equals to null pointer, and if we dot first rp dot first dot right is not equals to null pointer. Okay, if its left and right childs are null pointer, then we just need to add those nodes into our queue. So q dot p dot first left, rp dot se second minus 1. Similarly, q dot push rp dot first right, and rp dot second plus 1. So we have completed the code. Let's at last what we need to do, we just need to return the answer vector. Okay, because at last answer vector contains all those unique values which will be available to the user when he start looking from the top of a binary tree. So that's all for the code, and now we are going to run it, and if we encounter any error, we yeah, obviously we encounter the error, we try to resolve it. Okay, so the error we are getting is nothing, just because we have declared a variable here with the length name, and we are using the len variable. Okay, so let me rename it as with len. And the another error was we just forgot to create a new vector which stores our all the answers. So we have created it. Let's again try to run it, and yeah, it is accepted. Let's try to submit it. So the last thing which I'm trying to say, which I want to say, is that if you like this video, please hit the like button, share it with your friends, and don't forget to subscribe our YouTube channel. So that's all for this video. Let's meet in the next video. Till then, stay safe, stay healthy.